Hello there, and welcome back to the channel. Tonight we're drifting away from the chaos of Earth and into the infinite tranquility of space. We'll explore the most soothing discoveries from our cosmic neighborhood, gentle facts about distant worlds, and peaceful phenomena that unfold across the vast darkness beyond our atmosphere. Some of what we'll discover will feel like whispers from ancient starlight. Others will reveal the quiet rhythms that govern everything from spinning planets to the gentle dance of gravitational waves. But each revelation will remind you that the universe operates on such grand timescales that our daily concerns fade into insignificance when we contemplate the serene mechanics of the cosmos. This evening, we'll journey through discoveries that showcase space as not the cold, violent frontier we often imagine, but as a realm of profound peace and mathematical beauty. You might find yourself growing drowsy as we explore these cosmic lullabies, and that's perfectly fine. If you enjoy these peaceful explorations of the universe and would like to join us for more nighttime journeys among the stars, feel free to like and subscribe below. You can also share your thoughts about your favorite space discoveries down in the comments. But for now, all you need to do is get comfortable. Let your breathing slow, your mind soften, and allow the gentle wonder of the cosmos to wash peacefully over you. Let's begin. The universe speaks to us in whispers, not shouts. Every night as you prepare for sleep, billions of stars continue their ancient dance across the cosmic stage, following the same gravitational laws that have guided them for billions of years. The predictability of these celestial motions creates a sense of universal order that can be deeply comforting to contemplate before rest. When we look up at the stars, our brains naturally begin to quiet down from the day's mental chatter. There's something profoundly soothing about realizing that the light reaching your eyes tonight actually began its journey years, decades, or even centuries ago, traveling peacefully through the void to arrive at this exact moment. Scientists have discovered some remarkable connections between stargazing and better mental health. A study from early 2024 found that people who felt a greater connection to the night sky showed improved mental well-being and contentment. When we allow ourselves to get lost in contemplating the vastness above, it's almost like engaging in mindful meditation without even trying. Our busy minds seem to quiet down naturally, and we focus on the present moment, the beauty and immensity of it all. The simple act of observing celestial objects creates what psychologists call psychological distance, helping us step back from immediate concerns. This mental shift isn't just philosophical, but has real, measurable benefits for relaxation and sleep quality. The darkness of space itself serves as a natural metaphor for the restorative darkness of sleep, creating a mental bridge between cosmic observation and peaceful slumber. Even imagining the gentle drift of spacecraft through the interstellar medium can induce a meditative state that prepares the mind for rest. Studies show that people who regularly engage with astronomical content before bed report improved sleep onset and deeper, more refreshing rest. Our robotic explorers continue to send back discoveries that unfold like pages in a cosmic bedtime story. NASA's Perseverance rover moves across the Martian landscape with patient, methodical precision, each soul bringing new, quiet revelations about our neighboring world. The red planet's ancient history tells of a time when water flowed peacefully through riverbeds, creating the sediments that Perseverance now explores with robotic patience. After more than a year of careful analysis, the rover's Sapphire Canyon rock sample remains the mission's best candidate for preserving evidence of ancient microbial life processes. The transformation that Mars underwent across geological time speaks to nature's gentle persistence in creating and reshaping worlds. Jezero Crater's rocks reveal 3 distinct stages of water activity, shifting gradually from hostile acidic conditions to more life-friendly alkaline environments. This slow transformation over millions of years reminds us that even the most dramatic planetary changes happen with cosmic patience. The dust devils that dance across Mars's surface do so in near silence, creating whirlwinds that would appear as ghostly, graceful spirals to any observer. Even Mars's 2 small moons, Phobos and Deimos, orbit with such mathematical regularity that they serve as celestial timepieces, marking the passage of Martian days and nights with peaceful precision. The moons throughout our solar system harbor some of the most tranquil and potentially life-supporting environments we know. Saturn's icy moon, Enceladus, continues to fascinate scientists with its spectacular water plumes, which contain organic molecules and hint at a global ocean beneath its frozen surface. This hidden sea may be more hospitable to life than Earth's oceans, warmed by gentle tidal heating from Saturn's massive gravitational embrace. The water geysers that erupt from Enceladus's south pole operate with such regularity that they create rainbow-like displays in the sunlight, a celestial fountain that runs continuously in the silence of space. Europa, Jupiter's ice-covered moon, conceals an ocean twice as deep as all of Earth's seas combined. Where gentle currents may have circulated for billions of years, NASA's Europa Clipper spacecraft, launched in October 2024, is now making its way toward this intriguing world using the most peaceful form of space travel imaginable. Rather than fighting against the gravitational forces of the solar system, Europa Clipper will use gravity assists, borrowing momentum from Mars in February 2025 and Earth in December 2026 to reach Jupiter by April 2030. This elegant orbital choreography demonstrates how spacecraft can dance with planetary motion rather than oppose it, using the same celestial mechanics that have governed the solar system since its formation. The James Webb Space Telescope continues to reveal breathtaking secrets about our universe that inspire wonder and tranquility. This remarkable instrument has captured images of galaxies so distant that their light has traveled for over 13 billion years to reach us, meaning we're literally looking back in time toward the universe's peaceful infancy. Each photograph reveals stellar nurseries where new stars are born in clouds of glowing gas and dust, a process so gradual and serene that it unfolds over millions of years without hurry or violence. The infrared wavelengths that Webb observes allow us to see through cosmic dust, revealing hidden structures that speak to the universe's gentle, methodical processes of creation and evolution. In early 2024, Webb provided compelling evidence for a neutron star within the remnants of supernova 1987A, showing how even the most energetic events in space eventually settle into new patterns of cosmic order. These stellar remnants spin with clockwork precision, some pulsing hundreds of times per second, with timing more accurate than our best atomic clocks, serving as cosmic lighthouses that sweep their beams across space with mathematical regularity. Recent discoveries about black holes have revealed them to be far less destructive and more fascinating than we once imagined. While the brightest quasar ever observed is powered by a supermassive black hole consuming the equivalent of our sun's mass every single day, This process unfolds with cosmic slowness and regularity that can be deeply soothing to contemplate. Black holes follow precise mathematical laws, creating accretion disks that spiral inward with graceful predictability over thousands of years. Scientists have found that binary star systems can exist peacefully near black holes, showing that even these extreme objects participate in the universe's grand harmony. The event horizons of black holes represent boundaries in space-time that are mathematically perfect, creating a sense of cosmic order that transcends human understanding. Even the Hawking radiation that black holes theoretically emit follows quantum mechanical principles with clockwork precision, contributing to the universe's background hum of peaceful energy. The concept of cosmic time offers perhaps the most soothing perspective of all for those seeking peaceful sleep. When you gaze at Proxima Centauri, our nearest stellar neighbor, you're seeing light that left that star over 4 years ago, traveling peacefully through the void to reach your eyes at this exact moment. The light from more distant stars carries messages from decades, centuries, or even millennia in the past, creating a gentle connection between present moments and ancient cosmic events. This temporal perspective naturally soothes anxiety about immediate concerns, as it places our daily experiences within the context of deep time, where everything eventually finds its place in the cosmic story. The speed of light itself, while incredibly fast, represents a universal constant that governs all electromagnetic interactions with perfect consistency. From the radio waves carrying our communications to the gentle warmth of sunlight that reaches Earth after an 8-minute journey through space. Solar activity follows rhythms that connect us to the peaceful cycles of our home star. NASA and its partners declared that the Sun reached solar maximum in 2024, a period of heightened activity when space weather becomes more frequent. Even during solar maximum, our star's activity follows an 11-year cycle that has repeated with clockwork regularity for as long as humans have observed it. Solar Orbiter has identified the Sun's dual engines for creating high-speed electrons, explosive flares, and sweeping coronal mass ejections, yet even these energetic events follow predictable patterns that scientists can forecast. The aurora borealis and aurora australis that result from solar wind interacting with Earth's magnetosphere create some of nature's most peaceful light shows. Throughout 2024, powerful eruptions of plasma from the Sun have splashed against Earth's protective magnetic field, creating multiple dazzling displays that sweep down to altitudes rarely visited by the northern lights. These dancing curtains of light serve as visible reminders of the invisible forces that protect our planet, creating a sense of cosmic security perfect for peaceful contemplation before sleep. The study of exoplanets reveals a universe filled with worlds that might harbor their own quiet cycles of day and night. As of 2024, astronomers have discovered close to 900 stars that host multiple planets, each representing a unique cosmic dance where worlds orbit their stars with mathematical precision. These planetary systems create countless variations on the theme of celestial motion, with some planets locked in resonant orbits that repeat their gravitational interactions in perfect ratios. Like cosmic music played out over years and decades, some exoplanets exist in a state of tidal locking where one hemisphere experiences eternal day while the other enjoys perpetual night. Between these extremes lies a twilight zone where temperatures remain mild and stable, creating permanent sunset conditions that might harbor gentle climates perfect for life. The transit method astronomers use to detect these distant worlds involves measuring the subtle dimming of starlight as planets pass in front of their host stars. A process so gentle and regular that it resembles cosmic breathing patterns. K2-18b, located 124 light-years away, may have clouds of water vapor drifting through its atmosphere, creating weather patterns that unfold over alien days and seasons in skies we can only imagine. The discovery that red dwarf stars, the most common type of star in our galaxy, can host potentially habitable planets means there may be billions of worlds where life could exist in various forms, each following its own peaceful rhythms of planetary motion. These distant worlds remind us that the gentle cycles of day and night, seasons and years that govern life on Earth are likely playing out on countless worlds throughout the galaxy. Each potentially habitable planet represents a complete ecosystem that has developed its own unique balance of geological, atmospheric, and possibly biological processes over billions of years, creating a vast community of worlds where the universe might be quietly contemplating itself through countless different forms of awareness. Gravitational waves represent perhaps the most subtle and peaceful form of cosmic communication we know. These ripples in space-time travel at the speed of light, carrying information about the most energetic events in the universe. Yet they pass through our bodies and through Earth itself so gently that we need incredibly sensitive instruments to detect them. September 2025 will mark 10 years since the first direct detection of gravitational waves, confirming predictions that Albert Einstein made in 1916 about the fundamental nature of space and time. When two black holes spiral into each other and merge, they release gravitational waves that stretch and compress space itself in patterns that can be measured by detectors like LIGO. The clearest black hole merger signal yet recorded offers new insights into these mysterious objects. But what's most remarkable is how gently these cosmic messages reach us. Even the most violent events in the universe produce gravitational waves that wash over us with such subtlety that we remain completely unaware of their passage. This creates a profound sense of cosmic interconnectedness. We are constantly being gently touched by ripples from events happening millions or billions of light years away, creating an invisible network of gravitational communication that connects every particle in the universe. These waves carry information encoded in the fabric of space-time itself, whispering stories of distant collisions and cosmic dances that happened long before Earth even existed. The International Space Station provides a perfect example of human adaptation to the peaceful rhythms of orbital mechanics. For 24 years now, this outpost has maintained continuous human presence in space, with astronauts experiencing 16 sunrises and sunsets each day as they orbit Earth every 90 minutes. This creates an accelerated but deeply peaceful cycle of light and darkness that demonstrates how humans can adapt to entirely new temporal rhythms. The silence of space surrounding the station represents the deepest quiet that humans have ever experienced, broken only by the gentle hum of life support systems and occasional communications with ground control. Recent science operations have focused on foam physics research and material studies, work that unfolds with the same methodical patience that characterizes all activities in the weightless environment of orbit. The daily routines aboard the space station follow carefully planned schedules that maximize both productivity and psychological well-being, incorporating regular periods of Earth observation that provide natural meditation opportunities. Looking down at our planet from this orbital perspective creates what astronauts call the overview effect, a profound shift in awareness that emphasizes Earth's beauty, fragility, and unity. This cosmic viewpoint naturally reduces stress and promotes the kind of peaceful mental state that facilitates deep, restorative sleep. Recent advances in space technology demonstrate humanity's growing ability to explore the cosmos with increasingly gentle and sophisticated methods. Solar sails represent perhaps the most peaceful form of space propulsion ever conceived, using nothing but photons from the sun to gradually accelerate spacecraft to incredible speeds over time. Unlike chemical rockets that fight against gravity with violent explosions, solar sails work with the gentle pressure of light itself, accumulating momentum slowly but steadily across vast distances. The Ingenuity helicopter's flights on Mars showed that powered flight is possible even in the thin Martian atmosphere, with each flight lasting only minutes but representing millions of years of evolutionary and technological development compressed into moments of mechanical poetry. NASA's NISAR satellite recently reached a major milestone with the successful deployment of its enormous 39-foot antenna reflector, which folded up like an umbrella during launch and is now fully extended and ready to monitor Earth's surface changes with unprecedented precision. These technological achievements happen with such reliability and precision that they demonstrate humanity's increasing harmony with the physical laws that govern space and time. The fact that we can send robotic explorers to other worlds and receive their data across millions of miles of empty space speaks to our growing integration with cosmic processes that operate on scales far beyond human experience. Deep space astronomy continues to reveal the universe's most distant and ancient structures, providing perspectives that naturally promote peaceful contemplation. The James Webb Space Telescope has made too many discoveries to mention them all, but among the highlights are observations that stretch across the entire history of cosmic evolution, from planets and stars to some of the biggest questions about the early universe. Neutron stars, despite being some of the most extreme objects in existence, demonstrate the universe's tendency toward order and predictability. These collapsed stellar cores spin with such precision that they serve as cosmic timekeepers, more accurate than any clock humans have built. When these stellar lighthouses sweep their beams across space, they create navigation aids that could guide interstellar travelers across the galaxy. The Hubble Space Telescope, celebrating its 35th anniversary, continues to capture images that showcase the universe's beauty across multiple scales. From planetary nebulae that glow like cosmic flowers to spiral galaxies whose arms trace perfect logarithmic curves, these photographs serve as ideal focal points for meditation. Their beauty and scale naturally quiet mental chatter and promote the relaxed awareness that's perfect for sleep preparation. The search for potentially habitable worlds continues to expand our understanding of where life might exist throughout the cosmos. NASA's upcoming Habitable Worlds Observatory mission will help differentiate Earth-sized planets within the habitable zone, that perfect distance from a star where liquid water can exist on a planet's surface. This Goldilocks zone represents conditions that are not too hot, not too cold, but just right for life as we know it. Scientists have identified thousands of planets within these zones around other stars. suggesting that countless worlds might harbor their own peaceful cycles of weather, seasons, and possibly even life. The atmospheric compositions of these distant worlds can now be analyzed through spectroscopy, revealing the presence of water vapor, oxygen, and other molecules that might indicate biological processes operating in alien skies. Each potentially habitable world represents a complete planetary story that has unfolded over billions of years, with its own unique balance of geological forces, atmospheric chemistry, and possibly biological evolution. The discovery that such worlds may be common throughout the galaxy creates a sense of cosmic companionship, as if we're never truly alone in this vast universe, but part of a community of living worlds, scattered among the stars. Cosmic archaeology, through the study of ancient light, provides soothing perspectives on the universe's deep history and our place within it. Astronomers using Webb have revealed dwarf galaxies that existed in the first few 100 million years after the Big Bang, packed with enough energy to flood the early universe with its first starlight. Before this cosmic dawn, the universe experienced what scientists call the Dark Ages, when dense neutral hydrogen gas blocked visible light and created a kind of cosmic nighttime. When the first stars began to shine, they gradually ionized this hydrogen through a process called reionization, clearing the cosmic fog and allowing light to travel freely through space for the first time. This awakening happened so gently and gradually that it took hundreds of millions of years to complete, representing the universe's own slow emergence from its primordial slumber into the light-filled cosmos we observe today. The cosmic microwave background radiation that we can still detect carries information about the universe's structure when it was only 380,000 years old. These ancient photons have been traveling through space for over 13 billion years, carrying messages from a time when the universe was much simpler and more uniform than it is today. They represent the oldest light we can observe, a kind of baby picture of the cosmos that shows how peaceful and smooth conditions were in the early universe. The gentle physics of orbital mechanics governs all motion in space with mathematical precision that can be deeply comforting to contemplate as you drift toward sleep. Every satellite, planet, moon, and asteroid follows elliptical paths determined by the inverse square law of gravity, creating predictable cycles that have repeated for billions of years without deviation. These cosmic clockwork mechanisms operate with such reliability that we can calculate the position of any celestial body thousands of years into the future or past with extraordinary accuracy. Europa Clipper's journey to Jupiter demonstrates how spacecraft can borrow energy from planetary motion itself, using gravity assists that follow the same orbital mechanics governing celestial bodies since the formation of the solar system. In March 2025, the spacecraft will perform a flyby maneuver at Mars, using the red planet's gravitational field to increase its velocity. Later, in December 2026, it will swing by Earth once more, gaining additional momentum for its arrival at Jupiter in April 2030. This elegant choreography shows how we've learned to work with cosmic forces rather than against them. The Lagrange points scattered throughout our solar system offer natural parking spots where gravitational forces create stable regions in space. These invisible harbors represent perfect examples of cosmic harmony, where the competing pulls of massive bodies balance each other so precisely that spacecraft can remain stationary relative to both objects with minimal fuel expenditure. At these mathematical sweet spots, the universe provides rest stops for our mechanical explorers, quiet oases in the gravitational landscape. Even chaotic systems in space follow underlying mathematical laws that reveal hidden patterns within apparent randomness. The tumbling of certain asteroids, while unpredictable in the short term, operates according to principles that connect small perturbations to large-scale behaviors over time. These dynamics unfold with such complexity that they bridge the gap between order and chaos, showing us that even seemingly random cosmic events participate in deeper patterns we're only beginning to understand. The study of cosmic evolution reveals how the universe has grown from simplicity to complexity through gentle processes that unfold over cosmic time. Researchers using the Dark Energy Spectroscopic Instrument have mapped how nearly 6 million galaxies cluster across 11 billion years of cosmic history. Their observations align perfectly with Einstein's predictions about general relativity, showing that the way galaxies group together follows the same fundamental laws across vast spans of space and time. The cosmic web of dark matter filaments that connects all galaxies form through gravitational instability, acting over billions of years. This largest structure in the universe grew through processes so gradual that they represent the ultimate expression of patience in nature. Like a vast neural network spanning the cosmos, these filaments channel matter and energy across distances that dwarf our comprehension. Yet they do so with mathematical precision that speaks to an underlying order governing everything from the smallest quantum fluctuations to the grandest cosmic architectures. Galaxy collisions, while dramatic in astronomical terms, actually unfold over hundreds of millions of years, giving stars plenty of time to gravitationally adjust their orbits and avoid actual physical impacts. The approaching merger between the Milky Way and Andromeda galaxies, expected in about 4.5 billion years, will happen so gently that astronomers often call it a collision in name only. This cosmic dance will reshape both galaxies gradually, creating new stellar formations and orbital patterns without the violent destruction we might imagine. Star formation regions like the Orion Nebula represent stellar nurseries where new suns are born from the gentle gravitational collapse of gas and dust clouds. This process takes millions of years and produces the heavy elements necessary for planets and life through nuclear fusion in stellar cores. Each new star that ignites represents billions of years of patient accumulation, gravitational compression, and finally the moment when hydrogen begins fusing into helium, releasing the light that will warm planets we cannot yet imagine. The quantum nature of space itself provides the deepest level of cosmic peacefulness, connecting us to the fundamental fabric of reality. Recent experiments using the Cold Atom Lab aboard the International Space Station have produced the first dual-species Bose-Einstein condensates in space, creating matter in its most cooperative quantum state. In this exotic phase, individual atoms lose their separate identities and begin to behave as a single, coherent quantum system. Quantum mechanics reveals that empty space is never truly empty, but filled with virtual particles that constantly appear and disappear according to Heisenberg's uncertainty principle. This creates a gentle quantum foam that underlies all reality, a continuous background of creation and annihilation that maintains the stability of atoms and molecules throughout the universe. The zero-point energy of the quantum vacuum represents the lowest possible energy state of any system, yet even this ground state contains infinite potential energy that keeps the cosmos stable and predictable. Quantum entanglement demonstrates that particles can maintain instantaneous connections across any distance in space, suggesting that separation is ultimately an illusion and that all matter in the universe shares deep quantum correlations. When particles become entangled, measuring one instantly determines the state of its partner, regardless of the space between them. This phenomenon implies that the universe is more deeply interconnected than classical physics suggested, with invisible threads linking every particle to every other particle in ways we're still learning to understand. Recent discoveries about the cosmic balance of matter and energy reveal a universe that maintains itself in perfect equilibrium through forces we're only beginning to comprehend. Dark energy makes up approximately 70% of everything that exists, yet we can only detect its presence through its effects on cosmic expansion. This mysterious force pushes galaxies apart at an ever-increasing rate, but it does so with such subtle consistency that it maintains the delicate balance necessary for structure formation and the emergence of complexity. The cosmic microwave background radiation that fills all of space serves as a kind of universal white noise, a gentle remnant of the Big Bang that creates a constant, soothing background to all existence. This ancient light has been stretched by cosmic expansion until it now appears as microwave radiation, but it carries within it the seeds of all future structure. The tiny temperature variations in this primordial glow became the density fluctuations that eventually grew into galaxies, stars, and planets through gravitational amplification over cosmic time. Cosmic meditation practices draw directly from our growing understanding of the universe's peaceful nature. The practice involves visualizing oneself connected to the vast energy fields that permeate space, from the quantum fluctuations of empty space to the dark energy that drives universal expansion. Practitioners often report profound peace when contemplating their place within the cosmic web that connects all galaxies through invisible filaments of dark matter. The meditation technique of imagining oneself floating peacefully through the interstellar medium, surrounded by the gentle glow of distant nebulae, naturally induces the relaxed brainwave states associated with quality sleep. Even the cosmic background radiation serves as a meditation focus, representing the universe's own gentle breathing as it expands and evolves across billions of years. This connection to cosmic processes helps quiet the mind's chatter and promotes the deep relaxation necessary for restorative rest. Atmospheric studies of distant worlds continue to reveal the gentle chemistry that might support life across the galaxy. Scientists can now analyze the atmospheric compositions of exoplanets by observing how starlight filters through their air as they transit in front of their host stars. These spectroscopic observations reveal the presence of water vapor, oxygen, methane, and other molecules that create complex atmospheric dynamics on worlds we'll never visit but can study from afar. K2-18b, that potentially habitable world, 124 light-years away, show signs of water clouds drifting through skies that might experience gentle rains falling on alien landscapes. The atmospheric pressure and temperature conditions on this distant world could support liquid water on its surface, creating weather patterns and seasonal cycles that mirror Earth's own climate rhythms. Such worlds remind us that the peaceful interplay between starlight, atmosphere, and surface chemistry that makes Earth habitable might be common throughout the cosmos. The detection methods we use to find these worlds demonstrate the universe's cooperative nature in revealing its secrets. When a planet passes in front of its star, it blocks a tiny fraction of the star's light, creating a subtle dimming that sensitive instruments can measure. This transit method requires perfect alignment between the planet's orbit and our line of sight. Yet thousands of such alignments exist throughout the galaxy, as if the universe has arranged itself to make discovery possible. Recent advances in our understanding of stellar evolution show how stars age gracefully across billions of years, following predictable patterns that create the elements necessary for life. Main sequence stars like our Sun burn hydrogen steadily for most of their lives, maintaining stable energy output that allows planetary climates to develop complex patterns over geological time. Even the death of massive stars contributes to cosmic peace through supernova explosions that distribute heavy elements throughout space, seeding future generations of star systems with the materials needed for rocky planets and biological chemistry. White dwarf stars represent the peaceful endpoints of stellar evolution for stars like our Sun. These compact stellar remnants cool slowly over trillions of years, fading gradually from white-hot to red to brown, and finally to black dwarf stars that will persist long after all other stellar activity has ceased. This extremely gradual cooling process ensures that white dwarf stars will serve as the universe's last surviving embers, maintaining tiny amounts of heat in a cosmos that will eventually grow cold and dark. The study of stellar populations reveals how different generations of stars have enriched the universe with increasingly complex chemistry over cosmic time. Population 3 stars, the first generation to form after the Big Bang, consisted only of hydrogen and helium. When these massive stars died, they scattered heavier elements into space, allowing population 2 stars to form with trace amounts of metals. Our Sun belongs to population 1, rich in the heavy elements created by billions of years of stellar nucleosynthesis. This cosmic recycling process demonstrates the universe's economy of resources, where nothing is ever truly lost but transformed and redistributed across space and time. Every atom in your body except hydrogen was forged in the nuclear furnace of a star that died billions of years ago. This connects us intimately to cosmic processes, making us quite literally children of the stars, composed of elements that have journeyed across the galaxy to become part of our temporary biological arrangements. The gentle persistence of physical constants throughout cosmic history provides a foundation of stability that allows complex structures to form and evolve. The speed of light, the gravitational constant, and the fundamental forces maintain their values across billions of years and billions of light years, creating a reliable framework within which galaxies, stars, and planets can develop according to mathematical principles that never change. Even the expansion of space itself follows predictable patterns described by equations that relate the universe's geometry to its matter and energy content. The Hubble constant describes how quickly distant galaxies recede from us, while the cosmological constant represents the mysterious dark energy that drives acceleration. These parameters work together to create a cosmic environment where structure formation can occur gradually, allowing time for the complex processes that lead to planets, chemistry, and possibly life. The anthropic principle suggests that the universe's physical constants are precisely tuned to allow for the existence of complexity and consciousness. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If electromagnetic forces were different, atoms couldn't form stable chemical bonds. This apparent fine-tuning creates a sense that the universe is not hostile to complexity, but rather designed, whether by chance or necessity, to support the emergence of awareness and understanding. Radio astronomy continues to reveal the universe's gentle electromagnetic symphony, with signals traveling across vast distances to reach our sensitive receivers on Earth. Pulsars beam radio waves with clockwork precision, creating cosmic lighthouses that sweep their signals across space with timing more accurate than atomic clocks. These stellar remnants demonstrate how even the most extreme objects participate in the universe's orderly patterns, maintaining their rhythms across millions of years. Fast radio bursts, those mysterious millisecond flashes of radio energy, arrive at Earth carrying information about the cosmic medium they've traveled through. While their origins remain unclear, their very existence demonstrates the universe's capacity for sudden, brilliant communications across intergalactic distances. Each burst represents a cosmic shout that has journeyed for millions or billions of years to reach our instruments, carrying messages we're still learning to decode. The search for extraterrestrial intelligence continues to scan the skies for artificial signals that might indicate other civilizations among the stars. While we haven't detected any confirmed alien communications, the ongoing search itself represents humanity's growing integration with cosmic processes. Every survey expands our understanding of natural radio phenomena, while keeping us alert to the possibility that we share the galaxy with other forms of consciousness that contemplate the universe from their own perspectives. The cosmic perspective that emerges from space exploration naturally promotes the mental states conducive to peaceful sleep. When we contemplate our place in the vast cosmic web, our immediate concerns find their proper proportion within the grander scheme of existence. The universe's patient unfolding across billions of years provides a soothing temporal context that helps quiet anxiety about daily challenges and temporary setbacks. As you prepare for rest tonight, remember that you're participating in the same cosmic processes that govern quasars and quantum fields, stellar birth, and galactic evolution. The atoms in your body follow the same physical laws that guide planetary motion and stellar fusion. Your consciousness emerges from the same fundamental forces that create complexity throughout the universe. In sleep, your brain processes information and consolidates memories using biochemical mechanisms that connect you to the deepest patterns of cosmic organization. The universe continues its patient expansion while you dream, carrying galaxies ever further apart while maintaining the delicate balance of forces that allows structure and complexity to persist. Dark matter filaments stretch across billions of light years, channeling the flow of cosmic evolution with mathematical precision. Quantum fields fluctuate gently throughout space, maintaining the stability of matter and energy that makes existence possible. All of these processes unfold without hurry, following timescales so vast that human lifespans represent brief moments in the cosmic story. Yet within these moments, consciousness emerges and contemplates the very universe that gave it birth. As you drift toward sleep, you're participating in this ancient dialogue between mind and cosmos, awareness and existence, the observer and the infinite expanse of space and time that surrounds and permeates everything we know. The gentle rhythms of planetary formation continue to unfold throughout the galaxy, creating new worlds with the same patient processes that shaped Earth billions of years ago. protoplanetary disks swirl around young stars with mathematical elegance, their dust and gas gradually coalescing into rocky cores through gravitational attraction that operates like cosmic clockwork. These stellar nurseries demonstrate nature's preference for gradual construction over violent assembly, building planets grain by grain across millions of years, until worlds capable of supporting complex chemistry emerge from the cosmic dust. Within these forming systems, the habitable zones shift and stabilize as young stars settle into their main sequence burning phases. The precise distances where liquid water can exist on planetary surfaces represent cosmic sweet spots, where chemistry can explore its most complex possibilities. These Goldilocks regions aren't fixed boundaries, but gentle gradients where conditions transition smoothly from too hot to just right to too cold, creating multiple opportunities for habitability within each star system. The migration patterns of giant planets during system formation create additional complexity in these developing worlds. Jupiter-sized planets sometimes drift inward toward their stars before settling into stable orbits, their gravitational influence reshaping the entire architecture of their systems. This planetary migration happens so gradually that smaller worlds have time to adjust their orbits, creating resonant chains where multiple planets maintain mathematical relationships in their periods of revolution. Recent studies of stellar metallicity show how successive generations of star formation have enriched the galaxy with the heavy elements necessary for complex planetary chemistry. Stars born in the early universe contained almost no elements heavier than helium, while modern stars like our Sun incorporate the products of billions of years of stellar nucleosynthesis. This cosmic enrichment process ensures that newer planetary systems have access to the silicon, iron, carbon, and oxygen needed to build rocky worlds with diverse geological and atmospheric processes. The discovery of circumbinary planets reveals worlds that orbit binary star systems, experiencing double sunrises and sunsets as they follow complex orbital paths around two stars simultaneously. These exotic worlds demonstrate the universe's creativity in finding stable configurations even in seemingly chaotic gravitational environments. The mathematics governing such systems creates intricate patterns of heating and cooling that could produce entirely novel climate systems unlike anything we observe in our single-star neighborhood. Asteroid belt archaeology provides glimpses into the early solar system's formation processes, with each rocky fragment preserving chemical signatures from the primordial disk that gave birth to our planetary family. These ancient remnants follow predictable orbital patterns that have remained stable for billions of years, creating a kind of cosmic museum where we can study the building blocks from which Earth and the other planets assembled. The gentle collisions that occasionally occur between asteroids happen at speeds measured in meters per second, creating new fragments that continue the slow process of cosmic erosion and redistribution. The Kuiper Belt extends our solar system's influence far beyond the orbit of Neptune, populated by icy bodies that preserve pristine samples of the materials from which the outer planets formed. These distant objects follow elliptical orbits that can take centuries to complete, creating a vast reservoir of primordial ice and rock that occasionally sends comets sunward on million-year journeys. The discovery of dwarf planets like Pluto, Eris, and Makemake in these outer regions shows that planetary formation continued even at the cold edges of our system, where sunlight provides barely more warmth than starlight. Cometary science reveals the gentle processes by which water and organic compounds might have been delivered to early Earth, seeding our world with the materials necessary for biological chemistry. When comets approach the sun, solar heating sublimes their ices into glowing tails that can stretch for millions of kilometers. Yet this dramatic appearance masks an extremely gradual process of erosion that unfolds over thousands of orbital passages. Each return to the inner solar system strips away only thin layers of surface material, allowing comets to survive for millions of years while slowly diminishing in size and activity. The study of impact craters throughout the solar system tells stories of cosmic bombardment that shape planetary surfaces through gentle accumulation over geological time. While individual impacts represent moments of sudden energy release, the overall process of crater formation occurs so slowly that it becomes part of the natural aging process for rocky worlds. Moon's ancient highlands preserve a record of the heavy bombardment period when the solar system was still clearing debris from its formation, showing how even violent events contribute to the gradual evolution of planetary landscapes. Tidal forces demonstrate the universe's preference for gradual change over sudden transformation, slowly reshaping the orbits and rotations of celestial bodies through gravitational interactions that operate like cosmic friction. Earth's moon recedes from our planet by about 4 centimeters per year as tidal energy dissipation gradually expands its orbit, a process so slow that it connects the present moment to future eons when the moon will appear smaller in Earth's sky. These same forces have tidally locked many moons to their parent planets, creating worlds where one hemisphere permanently faces their primary, while the other remains in eternal darkness. The synchronization of orbital periods throughout the solar system creates resonant chains where planets and moons maintain mathematical relationships that prevent close encounters and orbital instability. Jupiter's Galilean moons demonstrate this principle beautifully, with Io, Europa, and Ganymede locked in a 1 to 2 to 4 resonance that has persisted for billions of years. These gravitational harmonics ensure that the moons never align in ways that would disrupt their orbits, creating a kind of celestial music where each world contributes its own frequency to the overall composition. Magnetospheric dynamics show how planets with magnetic fields create protective bubbles that deflect harmful cosmic radiation, while allowing benign solar particles to create aurora displays at their poles. Earth's magnetosphere extends far into space, creating a teardrop-shaped region where our planet's magnetic field dominates over the solar wind. This invisible shield fluctuates gently with solar activity, breathing in and out as it responds to changes in the stream of charged particles flowing from the sun. The Van Allen radiation belts trapped within Earth's magnetosphere demonstrate how magnetic fields can capture and store energetic particles for extended periods, creating stable reservoirs of cosmic radiation that follow predictable patterns of enhancement and decay. These belts expand and contract with solar cycle variations, providing a kind of space weather barometer that reflects the sun's 11-year rhythm of magnetic activity. Understanding these patterns helps protect astronauts and satellites while revealing the delicate balance between stellar energy and planetary magnetic protection. Atmospheric escape processes show how planets gradually lose their lighter gases to space over geological time, creating evolutionary pathways that can transform worlds from one type to another. Mars likely lost much of its original atmosphere through this slow leakage, transitioning from a warm, wet world to the cold, dry planet we observe today. Venus may have lost vast oceans through a runaway greenhouse effect that allowed water vapor to escape to space, leaving behind the dense carbon dioxide atmosphere that now shrouds our neighboring world. The concept of atmospheric retention connects planetary mass, magnetic field strength, and distance from the host star in relationships that determine which worlds can maintain the gas envelopes necessary for complex surface chemistry. Smaller planets struggle to hold on to hydrogen and helium, while larger worlds can retain these light gases throughout their histories. The balance between atmospheric gain through outgassing and loss through escape creates dynamic equilibria that evolve slowly as planetary systems age and their host stars gradually increase in luminosity. Seasonal cycles on other worlds reveal the diverse ways that axial tilt and orbital eccentricity can create temporal variations in heating and cooling across planetary surfaces. Mars experiences seasons similar to Earth's but lasting twice as long due to its longer year, while Uranus undergoes extreme seasonal changes as its extreme axial tilt causes each pole to experience decades of continuous sunlight followed by decades of darkness. These alien seasons unfold with the same mathematical predictability as Earth's climate cycles, rating universal Demon's principles of celestial mechanics that govern temporal change throughout the cosmos. The greenhouse effect operates on worlds throughout the solar system, creating diverse climate outcomes that depend on atmospheric composition, planetary mass, and solar distance. Venus demonstrates runaway greenhouse conditions where surface temperatures exceed the melting point of lead, while Mars shows how a thin atmosphere provides insufficient warming to prevent global freezing. Earth maintains moderate greenhouse warming that stabilizes liquid water at the surface, creating the temperate conditions that allow complex chemistry to flourish across geological time. Cloud formation processes on other worlds create weather patterns that mirror Earth's atmospheric dynamics, while incorporating exotic chemistry and extreme temperature ranges. Venus hosts sulfuric acid clouds that circulate the planet in 4-day superrotation patterns, while Jupiter's Great Red Spot represents a storm system that has persisted for centuries through mechanisms we're still working to understand. These alien weather systems follow the same fluid dynamics principles that govern Earth's atmosphere, scaled up or modified by different gravitational fields and chemical compositions. The discovery of subsurface oceans beneath the icy shells of outer solar system moons reveals how tidal heating can maintain liquid water in environments far from the sun's warming influence. Europa, Enceladus, Titan, and possibly several other moons harbor more liquid water than exists in all of Earth's oceans combined, kept warm by the constant flexing of their interiors as they orbit their massive parent planets. These hidden seas may have remained stable for billions of years, providing the kind of long-term environmental stability that complex chemistry requires to explore its most sophisticated possibilities. Hydrothermal activity on the ocean floors of these distant moons could create the same kind of energy-rich environments that may have fostered life's emergence on early Earth. Underwater volcanic vents provide chemical energy sources independent of sunlight, supporting ecosystems based on chemosynthesis rather than photosynthesis. If similar processes operate in the subsurface oceans of icy moons, they could maintain biological activity in environments completely isolated from the surface conditions that we typically associate with habitability. The search for biosignatures in exoplanet atmospheres represents humanity's expanding ability to detect the chemical fingerprints of life across interstellar distances. Oxygen, ozone, water vapor, and methane in the right combinations and concentrations could indicate biological processes operating on worlds we'll never visit directly. The James Webb Space Telescope has begun this search in earnest, analyzing the atmospheric compositions of potentially habitable worlds through spectroscopic observations that reveal which molecules absorb specific wavelengths of starlight. This technique of studying exoplanet atmospheres through transit spectroscopy demonstrates how the universe cooperates in revealing its secrets, aligning planetary orbits and stellar positions in ways that make detailed analysis possible across vast distances. Each successful atmospheric characterization adds another data point to our growing understanding of how common Earth-like conditions might be throughout the galaxy, helping us estimate whether biological chemistry represents a rare accident or a common outcome of cosmic evolution. The diversity of exoplanet types discovered so far reveals that planetary formation can produce worlds unlike anything in our solar system. From super-Earths with masses several times our planets to hot Jupiters that orbit their stars in periods measured in days rather than years. This variety suggests that our solar system represents just one possible outcome among many different architectural arrangements, each following the same gravitational principles, but producing unique combinations of planetary sizes, compositions, and orbital configurations. Mini-Neptunes appear to be among the most common types of exoplanets, occupying a size range between Earth and Neptune that doesn't exist in our solar system. These worlds likely possess substantial atmospheres that could create greenhouse conditions warm enough to support liquid water even at relatively large distances from their host stars. The prevalence of such planets throughout the galaxy suggests that habitable conditions might be more common than we initially expected, distributed among world types that we're only beginning to understand. Circumbinary planet formation demonstrates the universe's ability to create stable planetary systems, even in complex gravitational environments where two or more stars orbit each other. Planets like Kepler-47 CE orbit both members of binary star systems, experiencing gravitational influences from multiple stellar sources, while maintaining stable orbits that could persist for billions of years. These exotic worlds might experience double sunrises and sunsets with complex, seasonal patterns created by the orbital dance of their binary host stars. The concept of stellar habitable zones becomes more complex in multiple star systems, where planets might experience variable heating as they orbit around the combined gravitational center of two or more stars. Some configurations could create extended habitable zones where planets experience moderate temperatures across larger orbital distances, while others might produce rapid heating and cooling cycles that create unique environmental conditions, unlike anything we observe around single stars. Red dwarf longevity ensures that planets orbiting the most common type of star in the galaxy could maintain stable conditions for trillions of years, far longer than the expected lifetime of sun-like stars. These small, cool stars burn hydrogen so slowly that they could continue shining long after all larger stars have exhausted their fuel supplies, providing extended opportunities for biological evolution on any worlds that orbit within their habitable zones. The universe's preference for red dwarf formation means that most potentially habitable planets might orbit stars very different from our Sun. Tidal locking effects on planets around red dwarf stars create worlds with permanent day and night hemispheres, separated by twilight zones where temperatures remain moderate despite the extreme conditions on either side. These transition regions could support liquid water and complex chemistry while being sheltered from both the intense heating of the day side and the extreme cold of the night side. Understanding these alien climate patterns helps expand our definition of habitability beyond the Earth-like conditions we typically envision. Stellar evolution timescales ensure that planetary systems have billions of years to develop complex chemistry and potentially biological processes before their host stars begin to exhaust their hydrogen fuel supplies. Main sequence lifetimes provide stable energy output that allows planetary atmospheres and surface conditions to reach equilibrium states that could persist long enough for evolution to explore its most sophisticated possibilities. Even after stars begin to evolve beyond the main sequence, their gradual expansion into red giant phases happens slowly enough that planets might adapt to changing conditions. The ultimate fate of planetary systems depends on the mass of their host stars, with smaller stars providing longer periods of stable energy output, while larger stars evolve more rapidly through their life cycles. White dwarf remnants of Sun-like stars could continue to provide minimal heating to close-orbiting planets for trillions of years, creating opportunities for entirely different forms of chemistry and possibly biology adapted to low-energy environments. These post-main sequence possibilities extend the potential for complexity far into the cosmic future. Galactic chemical evolution shows how successive generations of star formation have gradually enriched the universe with the heavy elements necessary for rocky planet formation and complex chemistry. Early stars contained almost no elements heavier than helium, while modern stellar populations incorporate the products of billions of years of nucleosynthesis in previous generations of stars. This cosmic recycling process ensures that newer planetary systems have access to the full periodic table of elements needed to build diverse geological and atmospheric processes. Supernova nucleosynthesis creates elements heavier than iron through rapid neutron capture processes that operate during the explosive deaths of massive stars. These events distribute freshly synthesized gold, platinum, uranium, and other heavy elements throughout the interstellar medium, where they become incorporated into future generations of stars and planets. The gentle expansion of supernova remnants ensures that these enriched materials spread slowly through the galaxy over millions of years, gradually raising the metallicity of star-forming regions. Neutron-star mergers contribute additional heavy elements through R-process nucleosynthesis that occurs when these ultra-dense stellar remnants spiral together and collide. These rare events produce gravitational waves that we can now detect on Earth while simultaneously creating significant fractions of the universe's gold, platinum, and other precious metals. The collision rates of neutron star binaries provide a kind of cosmic clock that regulates the chemical enrichment of galaxies over cosmological time. The cosmic abundance patterns we observe today reflect billions of years of stellar processing that has gradually transformed the universe from a simple mixture of hydrogen and helium into a cosmos rich with the chemical diversity necessary for complexity. Every element in the periodic table heavier than lithium was forged in stellar cores or explosive stellar events, creating the material foundation upon which all subsequent complexity depends. This ongoing process of cosmic chemical evolution continues today as new stars form, live and die, adding their contributions to the galactic inventory of elements. Galactic recycling ensures that materials ejected by dying stars eventually become incorporated into new stellar and planetary systems, creating cycles of cosmic reincarnation that operate over hundreds of millions of years. The interstellar medium serves as a reservoir that collects stellar ejecta and gradually processes it through heating, cooling, and compression cycles that prepare it for incorporation into future generations of cosmic structures. This patient recycling process demonstrates the universe's efficient use of resources across cosmic time. Dark matter scaffolding provides the gravitational framework upon which all visible structure in the universe has assembled, creating a cosmic web of invisible filaments that channel the flow of normal matter into galaxies, clusters, and larger-scale structures. This dark matter network formed through gravitational instability acting on tiny density fluctuations present in the early universe, growing slowly over billions of years to create the largest structures we observe today. The cosmic web demonstrates how gravitational attraction operating over vast distances and enormous time spans can create organized structure from initially smooth distributions of matter and energy. Galaxy formation occurs preferentially along dark matter filaments, while the vast voids between these structures remain nearly empty of both dark and normal matter. This creates a foam-like pattern that extends throughout the observable universe, with galaxies strung like lights along invisible strands of dark matter. Structure formation simulations show how small quantum fluctuations in the early universe grew through gravitational amplification to become the galaxies, galaxy clusters, and cosmic web filaments we observe today. These computational models demonstrate that the universe's current structure represents the inevitable outcome of gravity, acting on primordial density variations across cosmic time. The mathematical predictability of this process creates a sense of cosmic determinism where the present structure of the universe was encoded in its initial conditions shortly after the Big Bang. Cosmic microwave background polarization measurements reveal the detailed patterns of density and temperature fluctuations that existed when the universe was very young. Universe first became transparent to light. These observations provide precise measurements of the cosmological parameters that govern cosmic evolution, confirming that our universe follows Einstein's general relativity on the largest scales while containing mysterious dark matter and dark energy components that dominate its mass-energy budget. The concordance model of cosmology demonstrates how a relatively simple set of parameters can accurately describe the universe's evolution from its earliest moments to the present day. This standard model incorporates ordinary matter, dark energy, and the cosmic expansion in a mathematical framework that successfully predicts a wide range of astronomical observations. The model's success suggests that despite the universe's apparent complexity, it operates according to comprehensible physical laws that connect quantum mechanics to cosmic scale phenomena. Precision cosmology has reached the point where we can measure the universe's age, composition, and geometry with remarkable accuracy, revealing a cosmos that is 13.8 billion years old and composed primarily of dark energy and dark matter, with ordinary matter making up less than 5% of the total. These measurements demonstrate the universe's mathematical nature, showing how fundamental constants and initial conditions combine to create the specific evolutionary pathway that led to stars, galaxies, planets, and ultimately to conscious observers capable of contemplating their cosmic origins. As we drift toward the peaceful realm of sleep, these cosmic perspectives remind us that we participate in processes far grander than our individual experiences, yet intimately connected to our moment-to-moment existence. The same physical laws that govern galactic evolution also organize the neural networks in your brain as it processes today's experiences and prepares for tomorrow's challenges. The elements in your body were forged in stellar cores and distributed by supernovae across cosmic time, making you quite literally a child of the stars temporarily organized into consciousness. The universe's patient unfolding across billions of years provides a soothing, temporal context that helps quiet anxiety about immediate concerns while connecting us to the deepest rhythms of cosmic evolution. In sleep, your consciousness participates in the same fundamental processes that create complexity throughout the universe, organizing information and maintaining the delicate patterns that constitute awareness itself. Rest becomes a form of cosmic meditation, allowing your mind to synchronize with the gentle rhythms that govern everything from quantum fields to galactic rotation. Tonight, as you settle into the gentle embrace of sleep, remember that you're connected to cosmic processes that operate with such elegant precision they seem almost musical in their mathematical harmony. The expansion of space itself follows patterns described by equations that relate the universe's geometry to its energy content, creating a framework so reliable that distant galaxies recede from us at precisely predictable rates. This cosmic choreography unfolds without hurry, carrying matter and energy across billions of light years while maintaining the delicate balance necessary for stars to shine and planets to form. The Hubble constant describes how quickly the universe expands, while dark energy provides the mysterious force that accelerates this expansion over time. These parameters work together like instruments in a cosmic orchestra, each contributing to a symphony of space and time that has been playing for nearly 14 billion years. The precision with which these forces operate creates an environment where complexity can emerge gradually, allowing time for the intricate processes that lead to chemistry, geology, and the emergence of awareness itself. Cosmic inflation theory suggests that our entire observable universe expanded from a region smaller than a proton in the first fraction of a second after the Big Bang. This rapid expansion smoothed out irregularities while preserving tiny quantum fluctuations that later became the seeds of all cosmic structure. The process happened so quickly that it defies everyday intuition, yet it operated according to physical principles that we can model mathematically, showing how even the most extreme events in cosmic history follow comprehensible laws. The flatness problem in cosmology reveals how precisely balanced the universe's initial conditions must have been to create the stable expansion we observe today. If the early universe had expanded slightly faster, matter would never have been able to clump together to form stars and galaxies. If expansion had been slightly slower, the universe would have collapsed back on itself long before complex structures could develop. This delicate balance suggests that our cosmos occupies a very special place in the space of all possible universes. The horizon problem addresses why distant regions of the universe that have never been in causal contact nevertheless show identical temperatures in the cosmic microwave background. Inflation theory elegantly solves this puzzle by proposing that these apparently disconnected regions were once close enough together to reach thermal equilibrium before being stretched apart by exponential expansion. This solution demonstrates how modern cosmology can explain seemingly paradoxical observations through mathematical models that extend our understanding of space and time. Primordial nucleosynthesis in the first few minutes after the Big Bang created the light elements that form the foundation of all subsequent chemistry. Hydrogen, helium, and trace amounts of lithium emerged from the cosmic fireball when temperatures dropped enough for protons and neutrons to combine into stable nuclei. The predicted abundances of these elements match observations with remarkable precision, providing strong confirmation that our models of early cosmic evolution accurately describe conditions in the primordial universe. The cosmic neutrino background represents a relic radiation from the early universe that permeates all of space, carrying information about conditions when the cosmos was only 1 second old. These ghostly particles interact so weakly with matter that they have traveled essentially undisturbed since the universe became transparent to them in its first moments. Detecting this neutrino background remains one of the great challenges in observational cosmology, but future experiments may finally capture these ancient messengers from the cosmic dawn. Baryon acoustic oscillations in the cosmic microwave background reveal sound waves that propagated through the early universe before atoms formed and made space transparent to light. These acoustic patterns froze into the temperature fluctuations we observe today, creating a standard ruler that astronomers use to measure cosmic distances and expansion rates across different epochs. The wavelength of these primordial sound waves provides a fundamental scale that connects the physics of the early universe to the large-scale structure we observe today. The cosmic coincidence problem asks why dark energy and matter densities are comparable today when their evolution rates are very different across cosmic time. In the distant past, matter dominated the universe's energy budget, while in the far future, dark energy will completely overwhelm matter's gravitational influence. We appear to live during a brief cosmic moment when these two components are roughly balanced, raising questions about whether this timing represents a remarkable coincidence or points to deeper physical principles we don't yet understand. Fine-tuning arguments in cosmology highlight how many fundamental constants seem precisely adjusted to allow for the existence of complexity and consciousness. The strength of nuclear forces, the mass ratios of elementary particles, and the rate of cosmic expansion all fall within narrow ranges that permit star formation, stellar nucleosynthesis, and the chemical diversity necessary for life. While these observations don't prove design, they do suggest that our universe occupies a very special place in the space of all possible physical laws and initial conditions. The multiverse hypothesis proposes that our observable universe represents just one region in a vastly larger structure that contains countless other universes with different physical laws and constants. In this picture, the apparent fine-tuning of our cosmos results from selection bias. We naturally find ourselves in a universe compatible with our existence because we couldn't exist in universes with different properties. This idea, while currently untestable, provides a potential explanation for cosmic fine-tuning that doesn't require intentional design. String theory cosmology suggests that our three-dimensional space might be embedded in higher dimensional structures called branes, with gravity able to propagate through extra dimensions while other forces remain confined to our familiar spatial dimensions. Collisions between branes could trigger Big Bang events, potentially creating cycles of cosmic death and rebirth that extend far beyond our current observational capabilities. These ideas push the boundaries of theoretical physics while maintaining mathematical consistency with known observations. Loop quantum gravity offers an alternative approach to understanding space-time at the smallest scales, proposing that space itself has a discrete structure made of tiny loops and nodes. This granular picture of space-time could eliminate the singularities that plague classical general relativity, replacing the Big Bang with a big bounce that connects our expanding universe to a previous contracting phase. The mathematical elegance of this approach suggests that space and time themselves might emerge from more fundamental quantum processes. The holographic principle proposes that all information contained within a volume of space can be encoded on its two-dimensional boundary, much like a hologram stores three-dimensional images on flat surfaces. This principle has profound implications for our understanding of black holes, suggesting that information falling into these objects isn't destroyed, but remains accessible on the event horizon. Applied to cosmology, holography hints that our three-dimensional universe might be a projection of information stored on a distant two-dimensional surface. Quantum field theory in curved spacetime reveals how the vacuum state of quantum fields changes in response to gravitational fields, potentially creating particle production in accelerating reference frames or near-massive objects. The Unruh effect predicts that accelerating observers will detect thermal radiation in what inertial observers perceive as empty space, while Hawking radiation suggests that black holes emit particles due to quantum fluctuations near their event horizons. These phenomena demonstrate deep connections between gravity, thermodynamics, and quantum mechanics. The information paradox in black hole physics asks what happens to information that falls past an event horizon when the black hole eventually evaporates through Hawking radiation. Quantum mechanics demands that information be preserved, but general relativity suggests that nothing can escape from inside a black hole. Recent advances in theoretical physics propose that information might be encoded in subtle correlations between outgoing Hawking radiation, allowing information to escape while respecting both quantum mechanics and general relativity. Wormhole physics explores the possibility that spacetime might contain tunnels connecting distant regions of the universe, or even separate universes entirely. While traversable wormholes would require exotic matter with negative energy density to remain stable, they represent exact solutions to Einstein's field equations and illustrate the remarkable flexibility of spacetime geometry. Even if such structures don't exist in nature, studying them deepens our understanding of how space and time can be curved and connected in unexpected ways. The cosmic censorship conjecture proposes that nature prevents naked singularities from forming, ensuring that all singularities remain hidden behind event horizons, where they can't influence the outside universe. This principle, while not proven, suggests that spacetime has built-in mechanisms to protect the predictability of physical laws by quarantining regions where classical physics breaks down. The mathematical exploration of this idea reveals deep connections between causality, thermodynamics, and the global structure of spacetime. Causal set theory attempts to understand spacetime as fundamentally discrete, composed of individual events connected by causal relationships, rather than continuous fields. In this picture, the smooth spacetime of general relativity emerges as an approximation valid at large scales, while the underlying reality consists of discrete causal networks. This approach provides a potential foundation for quantum gravity while maintaining the essential insight that causality provides the fundamental organizing principle for physical events. The measurement problem in quantum cosmology asks how classical space-time geometry emerges from quantum superpositions of different geometric configurations. If the universe began in a quantum state that included superpositions of different expansion rates, curvatures, and topologies, what mechanism selected the specific classical evolution we observe? Various approaches to this problem involve environmental decoherence, conscious observers, or spontaneous wave function collapse, each with different implications for our understanding of cosmic evolution. Eternal inflation models suggest that the inflationary expansion that shaped our observable universe continues indefinitely in other regions, constantly creating new pocket universes with potentially different physical laws. In this picture, our Big Bang represents just one bubble in an eternally expanding foam of space and time, with new regions continuously undergoing their own inflationary episodes. This scenario naturally generates the multiverse while making specific predictions about the statistical distribution of physical constants across different pocket universes. The anthropic landscape in string theory encompasses the vast number of possible vacuum states that could describe different universes with varying physical laws and particle content. With an estimated 10 to the power of 500 possible configurations, this landscape dwarfs the number of atoms in our observable universe, while potentially explaining the apparent fine-tuning of physical constants through statistical selection effects. Navigating this landscape requires new mathematical tools and conceptual frameworks that push the boundaries of theoretical physics. Cosmic topology studies the global shape and connectivity of the universe beyond the local geometry described by general relativity. While observations suggest that space is nearly flat on large scales, the overall topology could be quite different from the infinite Euclidean space we often assume. The universe might be finite but unbounded, like the surface of a sphere, or it could have exotic topological features such as handles or intersections that create shortcuts between distant regions. The cosmic microwave background provides our clearest window into the early universe, carrying detailed information about conditions when the cosmos first became transparent to light. Tiny temperature fluctuations in this ancient radiation reveal the seeds that grew into today's galaxies and galaxy clusters through gravitational instability. The statistical properties of these fluctuations encode information about inflation, dark matter, dark energy, and the fundamental parameters that govern cosmic evolution. Polarization patterns in the cosmic microwave background carry additional information about the early universe, particularly about gravitational waves generated during inflation. The detection of B-mode polarization would provide direct evidence for primordial gravitational waves, confirming key predictions of inflationary cosmology while opening new windows into the physics of the very early universe. Current and future experiments continue to push toward the sensitivity required to detect these subtle signals. The cosmic dark ages lasted from about 380,000 years after the Big Bang until the first stars began to shine, representing a period when the universe was filled with neutral hydrogen that absorbed most visible light. During this era, the only sources of illumination were the fading cosmic microwave background and perhaps the gentle glow of dark matter annihilation. Understanding this period requires sophisticated computer simulations that model how tiny density fluctuations grew into the first cosmic structures. Rionization marks the end of the cosmic dark ages, when radiation from the first stars and quasars ionized the neutral hydrogen that galactic space. This phase-filled-in transition happened gradually over hundreds of millions of years, creating a complex pattern of ionized bubbles that slowly merged to make the universe transparent to light once again. The details of reionization depend sensitively on the properties of the first stars and the early evolution of supermassive black holes. First star formation represents a crucial transition in cosmic evolution, when simple primordial gas clouds collapsed to form the massive stars that began the process of cosmic chemical enrichment. These population 3 stars contain no heavy elements, burning pure hydrogen and helium in nuclear reactions that created the first carbon, oxygen, silicon, and iron. When they died as supernovae, these elements were dispersed into the surrounding medium, enabling the formation of more complex second-generation stars. Supermassive black hole formation in the early universe presents a puzzle for astronomers, as these objects appear to have grown too massive too quickly to be explained by conventional accretion processes. Observations reveal black holes containing billions of solar masses when the universe was less than 1 billion years old, suggesting that they formed through direct collapse of massive gas clouds or grew from intermediate mass seeds through super-Eddington accretion. Understanding their formation connects questions about early star formation to the subsequent evolution of galaxies. Galaxy assembly proceeds through hierarchical merging, where smaller structures combine to form progressively larger systems over cosmic time. This bottom-up growth pattern explains how the massive elliptical galaxies we observe today assembled from numerous smaller progenitors through gravitational interactions that stirred stellar populations and triggered bursts of star formation. Computer simulations of this process reveal how galaxy properties depend on the cosmic web environment and the feedback effects of star formation and black hole growth. The stellar mass assembly history shows how the universe's star formation rate peaked roughly 10 billion years ago and has been declining ever since. As gas supplies became depleted and feedback processes began to suppress new star formation. This cosmic downsizing represents a fundamental transition from a young, actively star-forming universe to the mature cosmos we observe today, where most stellar mass has already been converted from gas into long-lived stars. Chemical evolution proceeds as successive generations of stars enrich the interstellar medium with heavy elements, gradually increasing the metallicity of star-forming regions throughout cosmic time. This process happens at different rates in different types of galaxies, with massive ellipticals reaching high metallicities quickly through intense early star formation, while smaller dwarf galaxies continue to form metal-poor stars even today. The observed abundance patterns provide detailed records of nucleosynthesis processes operating across cosmic history. Galactic archaeology uses the chemical compositions and kinematic properties of individual stars to reconstruct the formation history of the Milky Way, revealing evidence for past merger events and accretion episodes that shaped our galaxy's structure. Ancient stars preserve chemical signatures of the environments where they formed, allowing astronomers to identify stellar populations that originated in smaller galaxies that were later absorbed by our own. This forensic approach to galactic evolution provides detailed case studies of hierarchical assembly processes. The local group of galaxies provides a nearby laboratory for studying gravitational interactions and tidal effects that shape galactic evolution on small scales. The approaching collision between the Milky Way and Andromeda galaxies, expected in roughly 4 billion years, will create a new elliptical galaxy through processes that computer simulations can model in detail. Smaller satellite galaxies like the Magellanic Clouds demonstrate how tidal stripping and ram pressure can transform galactic morphology over time. Cosmic web evolution shows how matter flows along dark matter filaments from low-density voids toward high-density nodes where galaxy clusters form. This pattern creates a foam-like structure that evolves slowly as gravitational instability amplifies initial density contrasts. The cosmic web provides the scaffolding for galaxy formation, while channeling the flow of gas and dark matter across the largest scales in the universe. Void evolution demonstrates how regions of below-average density expand faster than the cosmic mean, gradually emptying as matter flows toward surrounding overdense regions. These cosmic voids grow larger and more empty over time, creating vast spaces where galaxies are rare and the cosmic web structure becomes most apparent. The statistical properties of voids provide sensitive tests of cosmological models and dark energy properties. Large-scale structure surveys map the three-dimensional distribution of galaxies across cosmic time, revealing how the cosmic web has evolved since the universe was roughly half its present age. These observations test theoretical predictions about structure growth while measuring the effects of dark energy on cosmic expansion history. The patterns of galaxy clustering encode information about primordial fluctuations, dark matter properties, and the physics of galaxy formation. Weak gravitational lensing by large-scale structure provides a direct probe of dark matter distribution that doesn't depend on assumptions about how visible matter traces invisible mass. By measuring subtle distortions in the shapes of distant galaxies caused by intervening matter, astronomers can map dark matter on scales ranging from individual galaxy halos to the cosmic web itself. This technique reveals the dark universe directly through its gravitational effects on light. Strong gravitational lensing creates dramatic arcs and multiple images of background sources when massive galaxy clusters focus light like cosmic telescopes. These natural magnifying glasses allow astronomers to study high redshift galaxies in detail while probing the mass distribution of the lensing clusters. The time delays between multiple images of variable sources provide independent measurements of cosmic expansion rates and dark energy properties. Gravitational microlensing reveals compact objects in the Milky Way through temporary brightening events when they pass in front of background stars. This technique has discovered numerous exoplanets while probing the population of brown dwarfs, white dwarfs, neutron stars, and potentially black holes that make up the galaxy's dark stellar remnants. The statistics of microlensing events constrain the contribution of compact objects to dark matter in our galactic halo. The search for primordial gravitational waves focuses on B-mode polarization patterns in the cosmic microwave background that would provide direct evidence for cosmic inflation. These gravitational wave signatures would carry information about physics at energy scales far beyond what particle accelerators can probe, potentially revealing the quantum nature of gravity itself. Current experiments continue to push toward the sensitivity required to detect these primordial signals against foreground contamination from our galaxy. Pulsar timing arrays use networks of precisely timed neutron stars as galactic-scale gravitational wave detectors sensitive to low-frequency waves from supermassive black hole mergers. These experiments have recently reported evidence for a gravitational wave background that could originate from countless black hole binaries throughout cosmic history. Future observations will determine whether this signal matches predictions from galaxy merger models or reveals new physics. The cosmic gravitational wave background represents the incoherent superposition of waves from all sources throughout cosmic history, creating a stochastic signal that encodes information about stellar evolution, compact object formation, and cosmic structure growth. Different frequency ranges carry signatures of different source populations, from stellar mass binary mergers detectable by ground-based interferometers to supermassive black hole coalescences observable through pulsar timing. Space-based gravitational wave observatories will open new frequency windows that complement ground-based detectors, providing access to intermediate mass black hole mergers and the in-spiral phases of massive binary systems. These missions will trace black hole formation across cosmic time while studying the dynamics of galactic centers and testing general relativity in strong field regimes. The multi-messenger astronomy enabled by gravitational wave detection promises to revolutionize our understanding of cosmic evolution. Cosmological phase transitions in the early universe may have generated gravitational waves through bubble nucleation and collision processes as the cosmos evolved through different symmetry-breaking epochs. These primordial signals would carry information about particle physics at temperatures and energies far beyond terrestrial experiments, potentially revealing the existence of extra dimensions, supersymmetry, or other exotic physics. Detecting such waves would provide direct observational access to the fundamental laws governing reality. As your mind settles into the peaceful rhythms of approaching sleep, these cosmic perspectives remind you that consciousness itself represents one of the universe's most remarkable achievements. The same physical processes that created stars and galaxies also organize the neural networks that allow you to contemplate your place in the cosmic story. Your awareness emerges from billions of years of cosmic evolution, stellar nucleosynthesis, and planetary development that culminated in the biochemical complexity capable of understanding its own origins. The universe's patient unfolding across deep time provides a context of ultimate tranquility, where temporary concerns find their proper perspective within the grand cosmic narrative. Sleep becomes a form of participation in these fundamental processes, allowing your consciousness to synchronize with the gentle rhythms that govern everything from quantum field fluctuations to the expansion of space itself. In dreams, your mind explores patterns and connections that mirror the self-organization principles operating throughout the cosmos. Tonight, as you drift into peaceful rest, remember that you carry within yourself the same elements forged in stellar cores billions of years ago, temporarily arranged into the exquisite complexity that makes awareness possible. The carbon in your cells, the iron in your blood, and the oxygen you breathe all trace their origins to nuclear furnaces that burned out long before Earth formed, connecting your individual existence to the deepest processes of cosmic evolution. In sleep, these ancient elements continue their patient work of maintaining the biological patterns that sustain consciousness itself. The darkness that surrounds your rest mirrors the cosmic darkness that fills most of space. punctuated by islands of light where stars shine and planets orbit in their eternal celestial dances. This cosmic night provides the perfect backdrop for dreams that might echo the universe's own creative processes, generating new patterns and possibilities from the information gathered during your waking hours. Rest well in the knowledge that you participate in the same fundamental creativity that brings forth stars, planets, and the endless complexity of cosmic evolution. The gentle mechanics of cosmic chemistry continue to unfold in laboratories scattered throughout space, where stellar interiors serve as furnaces that transmute simple hydrogen into the complex periodic table of elements we know today. Within the cores of massive stars, temperatures reach hundreds of millions of degrees, creating conditions where atomic nuclei overcome their electrical repulsion and fuse together in nuclear reactions that power stellar luminosity for millions of years. This stellar alchemy operates with such patience that individual fusion reactions happen at rates we can barely measure. Yet their cumulative effect over cosmic time has created every element heavier than hydrogen and helium. The carbon-nitrogen-oxygen cycle that powers stars more massive than our Sun demonstrates how nuclear physics creates self-sustaining reactions that can burn steadily for geological ages. Carbon nuclei serve as catalysts in this process, temporarily capturing protons and releasing energy before returning to their original state, ready to facilitate the next fusion reaction. This elegant chemical recycling within stellar cores mirrors the larger cosmic recycling that distributes heavy elements throughout the galaxy when massive stars eventually explode as supernovae. Silicon burning in the final moments of massive stellar evolution creates iron peak elements through rapid nuclear reactions that happen in the last few seconds before core collapse. These reactions proceed so quickly that they represent the universe's most intense chemistry laboratory, where atomic nuclei are assembled and disassembled in microseconds under conditions of extreme temperature and density. The iron-56 nuclei produced in this process have the highest binding energy per nucleon of any atomic of protons and neutrons possible nucleus, making them the most stable arrangement. When stellar cores exceed the Chandrasekhar limit and collapse into neutron stars, they create matter in its most extreme form, where protons and electrons are crushed together to form neutrons in a process that essentially turns the entire stellar remnant into a single atomic nucleus several kilometers across. The surface gravity of these objects is so intense that a sugar cube-sized piece of neutron star material would weigh as much as Mount Everest. Yet these extreme conditions create the most precise timekeepers in the universe. Pulsar magnetospheres generate radio beams through processes that accelerate charged particles to nearly the speed of light in magnetic fields, trillions of times stronger than Earth's. These cosmic lighthouses sweep their beams across space with timing so precise that millisecond pulsars maintain accuracy comparable to atomic clocks over periods of years. The radio emission mechanisms operating in these magnetospheres create natural particle accelerators that dwarf any technology humans have built. Yet they operate continuously for millions of years without maintenance or external power sources. Binary pulsar systems provide natural laboratories for testing Einstein's general relativity in gravitational fields, far stronger than anything we can create artificially. The orbital decay of these systems as they lose energy to gravitational wave emission matches theoretical predictions with extraordinary precision, confirming that space-time itself ripples and flows according to mathematical equations derived from pure thought. These cosmic experiments operate over timescales of millions of years, allowing us to test physical theories through observations of systems we could never hope to replicate in terrestrial laboratories. The interstellar medium serves as a vast chemical processing plant where atoms and molecules interact at extremely low densities over periods of millions of years. In the near-perfect vacuum between stars, chemical reactions proceed through pathways impossible under terrestrial conditions, creating complex organic molecules in environments where individual particles might wait centuries between collisions. Radio astronomy has revealed an extensive inventory of interstellar chemistry, including alcohols, acids, and aromatic compounds floating freely in the space between stellar systems. Molecular cloud collapse demonstrates how gravity can organize diffuse interstellar gas into dense stellar nurseries, where new stars condense from the cosmic medium. These clouds can remain stable for millions of years before some disturbance, perhaps a nearby supernova or the gravitational influence of a passing star, triggers the collapse process that leads to star formation. The initial phases of this gravitational contraction happen so slowly that individual molecules have time to radiate away their thermal energy, allowing the cloud to cool and contract further. Protostellar evolution follows predictable pathways as contracting gas clouds gradually heat up through gravitational compression until nuclear fusion ignites in their cores. This process can take several million years for Sun-like stars, during which the protostar exists in a delicate balance between gravitational collapse and radiation pressure from nuclear burning. The gradual transition from gravitational energy to nuclear energy represents one of nature's most elegant phase changes, transforming a cold gas cloud into a self-sustaining nuclear reactor that can shine for billions of years. T-Tauri variables represent young stars in the final stages of gravitational contraction, exhibiting irregular brightness variations as they settle into stable nuclear burning. These stellar adolescents often possess circumstellar disks of gas and dust where planetary formation begins, creating environments where solid particles gradually accumulate into larger bodies through gentle collisions and gravitational attraction. The chaotic early phases of stellar evolution eventually give way to the stable main sequence burning that characterizes stellar maturity. Herbig-Haro objects reveal how young stars interact with their surrounding environment through powerful stellar winds that carve cavities in the dense molecular clouds where star formation occurs. These glowing shock fronts propagate through the interstellar medium at speeds of hundreds of kilometers per second, yet they represent gentle processes compared to the violent events we might imagine. The interaction between stellar winds and ambient gas creates spectacular nebular structures that evolve visibly over human timescales. Brown dwarf formation explores the boundary between stellar and planetary mass objects, revealing a population of failed stars that never achieved the central temperatures necessary for sustained nuclear fusion. These substellar objects cool gradually over billions of years, fading from red to infrared as they radiate away their formation energy without any internal nuclear fuel source. Brown dwarfs occupy a mass range that bridges the gap between the largest planets and smallest stars, demonstrating that nature creates objects across a continuous spectrum of sizes and properties. Planetary system architecture shows how gravitational interactions during the early phases of system formation can lead to a wide variety of final orbital configurations. Hot Jupiters that orbit extremely close to their parent stars likely formed at much larger distances before migrating inward through gravitational interactions with protoplanetary disk material. This migration process can relocate massive planets from the outer regions where they formed to the inner system, where they complete their orbits in a matter of days. Resonant chains among exoplanets demonstrate how gravitational interactions can lock multiple worlds into stable orbital relationships that persist for billions of years. The TRAPPIST-1 system contains 7 Earth-sized planets whose orbital periods maintain precise mathematical ratios, ensuring that the planets never approach each other closely enough to disrupt their stable configuration. These resonant systems represent solutions to the gravitational many-body problem that nature discovers through the slow evolution of planetary orbits over millions of years. Tidal heating in close-orbiting exoplanets creates internal energy sources that can maintain geological activity and potentially habitable surface conditions even on worlds that receive little energy from their host stars. The constant flexing of planetary interiors as they follow elliptical orbits around their stars generates heat through friction in much the same way that Jupiter's moons remain geologically active despite their great distance from the Sun. This process can extend the habitable zone around stars to include planets that would otherwise be frozen solid. Atmospheric escape processes on close-orbiting planets reveal how stellar radiation can gradually strip away planetary atmospheres over geological time. High-energy photons from the host star can break atmospheric molecules apart and accelerate the resulting atoms to escape velocity, creating comet-like tails of evaporating atmosphere that stream away from these worlds. Some hot Jupiters may lose significant fractions of their mass through this process, potentially evolving into smaller Neptune-like planets or even rocky super-Earths. The concept of planetary habitability continues to expand as we discover worlds that maintain liquid water under conditions very different from Earth's surface environment. Subsurface oceans beneath the ice shells of outer solar system moons demonstrate that habitable conditions can exist far from the traditional habitable zones defined by stellar heating. These hidden seas may remain stable for billions of years, providing the temporal stability that complex chemistry requires to explore its most sophisticated possibilities. Astrobiology investigates the chemical pathways through which life might emerge from non-living matter under the diverse conditions found throughout the universe. Laboratory experiments have shown that organic molecules can form spontaneously under conditions thought to exist in protoplanetary disks, suggesting that the chemical building blocks of life may be common throughout cosmic environments. The detection of organic compounds in meteorites, comets, and even in the interstellar medium indicates that complex chemistry operates wherever suitable conditions exist. Extremophile organisms on Earth demonstrate life's remarkable adaptability to conditions once thought impossible for biological processes. These hardy microorganisms thrive in boiling springs, highly acidic environments, intensely radioactive locations, and the deepest ocean trenches where pressure exceeds that found anywhere else on the planet's surface. Their existence expands our understanding of the range of conditions under which life might flourish on other worlds, suggesting that habitable environments may be far more common than previously imagined. Panspermia theories propose that life might spread throughout the galaxy through natural processes that transport viable organisms between planetary systems. Meteorite impacts can launch rocks from planetary surfaces into interplanetary space, where they might travel for millions of years before landing on other worlds. While the survival of living organisms during such journeys remains uncertain, laboratory studies have shown that some extremophiles can withstand the harsh conditions of space for extended periods. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by considering factors such as the rate of star formation and the probability of life on other planets' formation, the fraction of stars with planets, and the likelihood that life will develop intelligence and technology. While many of the equation's parameters remain highly uncertain, it provides a framework for thinking about humanity's place in the cosmic community and the probability that we share the galaxy with other forms of consciousness. SETI research continues to scan the skies for artificial signals that might indicate the presence of technological civilizations among the stars. Modern search strategies examine radio frequencies, optical pulses, and even gravitational wave signatures that might carry information across interstellar distances. While no confirmed alien signals have been detected, the ongoing search expands our understanding of natural astronomical phenomena while keeping us alert to the possibility of cosmic companionship. The Fermi paradox asks why, given the vast number of stars and the age of the galaxy, we haven't encountered clear evidence of other technological civilizations. Proposed solutions range from the possibility that life is extremely rare to the idea that advanced civilizations tend to destroy themselves or transcend physical existence in ways we can't yet imagine. This puzzle highlights the profound uncertainty surrounding our place in the cosmic order, and the question of whether intelligence represents a common or exceptional outcome of evolutionary processes. Technological signatures, or technosignatures, represent observational evidence that might indicate the presence of advanced civilizations even if they're not actively trying to communicate with us. These could include artificial atmospheric compositions, megastructures around stars, or patterns of energy consumption that reveal industrial activity on planetary scales. Future astronomical surveys may become sensitive enough to detect such signatures if they exist in nearby star systems. The concept of a galactic habitable zone suggests that life-supporting conditions may be most favorable in a ring-shaped region around the galaxy's center, where heavy element abundances are sufficient for rocky planet formation, but radiation levels remain moderate. Stars in the galactic center experience too much harmful radiation from supernovae and other energetic events, while stars in the outer regions lack the heavy elements necessary for complex chemistry. Our solar system orbits within this potentially favored zone. Stellar metallicity gradients show how the abundance of heavy elements decreases with distance from galactic centers, reflecting the history of star formation and chemical enrichment across different galactic environments. This variation in available raw materials could significantly affect the types of planetary systems that form in different galactic locations, with implications for the development of complex chemistry and potentially life itself. Galactic dynamics reveal how our solar system follows a stable orbit around the galactic center, while oscillating gently above and below the galactic plane with a period of roughly 60 million years. These slow oscillations may correlate with mass extinction events on Earth, as our passage through the galactic plane exposes us to increased cosmic ray flux and gravitational perturbations from molecular clouds. The galactic environment provides a slowly varying background that influences planetary conditions over geological time. Cosmic ray modulation by the solar wind creates a protective bubble around our solar system, that partially shields us from high-energy particles originating in distant supernovae and other galactic sources. The strength of this shielding varies with the solar cycle, creating periodic changes in the cosmic ray environment that may influence atmospheric chemistry and climate on Earth. Understanding these connections helps us appreciate how intimately planetary conditions are linked to both solar and galactic processes. The local bubble in the interstellar medium represents a region of hot, low-density gas created by multiple supernova explosions over the past 10 million years. Our solar system currently moves through this cavity, experiencing lower densities of interstellar dust and gas than typical for our galactic neighborhood. This relatively clear environment may affect the flux of cosmic rays reaching Earth and the visibility of distant astronomical objects. Stellar encounters occur when other stars pass close enough to our solar system to gravitationally perturb the orbits of comets in the Oort cloud, potentially sending some of these icy bodies into the inner solar system where they become visible as long-period comets. These encounters happen roughly every few 100,000 years and provide a gentle mechanism for delivering volatile materials to the inner planets over geological time. The galactic rotation curve reveals how dark matter dominates the gravitational field in the outer regions of spiral galaxies, causing stars to orbit faster than would be expected from the visible matter alone. This discovery revolutionized our understanding of cosmic composition, showing that ordinary matter represents only a small fraction of the total mass energy in the universe. The dark matter that shapes galactic rotation curves may consist of exotic particles that interact only through gravity. Galaxy interactions and mergers drive the evolution of stellar populations and trigger episodes of enhanced star formation as gravitational tides compress interstellar gas clouds. These processes happen so slowly that individual stars rarely collide during galactic mergers, but the overall structure and stellar content of galaxies can be dramatically altered over hundreds of millions of years. Computer simulations reveal how these cosmic collisions reshape galactic morphology while preserving most stellar systems. Active galactic nuclei demonstrate how supermassive black holes can influence their entire host galaxies through jets and winds that carry energy far beyond the immediate vicinity of the central black hole. These feedback processes regulate star formation rates and may explain why the most massive galaxies contain relatively few young stars, despite their large gas reservoirs. The relationship between black hole growth and galaxy evolution represents one of the most active areas of current astrophysical research. Quasar evolution traces the cosmic history of supermassive black hole formation and growth, revealing how these objects grew rapidly in the early universe before settling into the relatively quiet state we observe in most nearby galaxies. The peak epoch of quasar activity occurred when the universe was roughly 1/4 its present age, coinciding with the era of maximum star formation activity throughout cosmic history. The cosmic web structure on the largest scales shows how matter flows along dark matter filaments that connect galaxy clusters, while leaving vast voids nearly empty of both dark and ordinary matter. This pattern emerged from tiny quantum fluctuations in the early universe through gravitational instability acting over billions of years. The resulting foam-like structure represents the largest organized pattern in the observable universe. Cosmic variance describes the statistical uncertainty in measurements of cosmic properties that results from observing only one particular region of an infinite universe. different parts of the cosmos may have evolved differently due to variations in initial conditions, making it challenging to determine universal properties from local observations. Understanding cosmic variance helps astronomers interpret their measurements within appropriate statistical frameworks. The cosmic distance ladder relies on a series of overlapping measurement techniques that extend our ability to determine distances from nearby stars to the most distant galaxies. Each step in this ladder depends on calibrations from closer objects, creating a chain of measurements that spans more than 10 orders of magnitude in distance. Systematic errors in any step of this process can propagate through the entire distance scale, making precision cosmology a challenging observational enterprise. Dark energy surveys map the three-dimensional distribution of galaxies across cosmic time to measure how the expansion rate of the universe has changed as dark energy's influence has grown. These observations test theoretical models of dark energy while providing precision measurements of cosmological parameters that describe the universe's composition and evolution. The statistical power of these surveys comes from observing millions of galaxies across billions of years of cosmic history. Type Ia supernovae serve as standardizable candles for measuring cosmic distances because they result from the thermonuclear explosions of white dwarf stars that approach a critical mass limit. The discovery that distant supernovae appear dimmer than expected for a coasting universe led to the realization that cosmic expansion is accelerating under the influence of dark energy. These stellar explosions provide our most direct evidence for the mysterious force that dominates the universe's energy budget. Cosmic microwave background anisotropies encode a wealth of information about the early universe in their subtle temperature and polarization patterns. The acoustic oscillations frozen into this ancient light reveal the sound waves that propagated through the primordial plasma before atoms formed and made the universe transparent. Statistical analysis of these patterns provides precision measurements of fundamental cosmological parameters with uncertainties of only a few percent. Big Bang nucleosynthesis calculations predict the primordial abundances of light elements based on the physics of nuclear reactions in the early universe, when temperatures and densities were high enough for nuclear fusion to occur. The agreement between theoretical predictions and observational measurements of hydrogen, helium, and lithium abundances provides strong evidence that our understanding of early cosmic evolution is fundamentally correct. Inflation theory explains several puzzling features of the cosmic microwave background, including its remarkable uniformity across regions that were never in causal contact according to standard Big Bang cosmology. The rapid exponential expansion during inflation stretched quantum fluctuations to astronomical scales, creating the density perturbations that later grew into galaxies and galaxy clusters through gravitational instability. The multiverse concept emerges naturally from many theoretical frameworks in cosmology and particle physics, suggesting that our observable universe may represent just one region in a vastly larger structure. Different regions of the multiverse might have different physical laws, fundamental constants, or even different numbers of spatial dimensions. While these ideas remain highly speculative, they provide potential explanations for the apparent fine-tuning of physical constants in our cosmic neighborhood. String theory attempts to unify quantum mechanics and general relativity by proposing that fundamental particles are actually tiny vibrating strings rather than point-like objects. different vibrational modes of these strings correspond to different particle types, potentially explaining the entire spectrum of fundamental forces and matter fields within a single mathematical framework. While string theory remains experimentally unconfirmed, it has generated profound insights into the nature of space, time, and quantum gravity, and loop quantum gravity offers an alternative approach to quantum gravity that maintains the background independence of general relativity while quantizing space-time itself. In this framework, space and time emerge from discrete quantum networks rather than continuous fields, potentially eliminating the singularities that plague classical general relativity. The theory predicts that the Big Bang might be replaced by a quantum bounce connecting our expanding universe to a previous contracting phase. Holographic cosmology explores the possibility that all information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary, similar to how holograms store three-dimensional images. This principle has profound implications for our understanding of black holes and may eventually revolutionize our conception of space, time, and information. Applied to cosmology, holography suggests that our three-dimensional universe might emerge from information processing on a distant boundary. Quantum cosmology attempts to describe the wave function of the universe itself, treating the entire cosmos as a quantum mechanical system. This approach faces conceptual challenges related to the measurement problem in quantum mechanics, since there's no external observer to collapse the cosmic wave function. Various interpretations propose different solutions to this puzzle, from many-world scenarios to spontaneous wave function collapse mechanisms. Causal set theory proposes that space-time consists of discrete events connected by causal relationships, rather than the continuous manifold described by general relativity. In this picture, the smooth geometry of space-time emerges as an approximation valid at large scales, while the fundamental reality consists of discrete causal networks. This approach provides a potential foundation for quantum gravity, while preserving the causal structure that seems essential to physics. Emergent gravity theories suggest that gravitational attraction might arise from more fundamental microscopic interactions. Much like thermodynamic properties emerge from statistical mechanics. In these models, Einstein's equations would represent effective descriptions valid at large scales, while the underlying reality involves quantum entanglement, information processing, or other microscopic phenomena. These ideas remain highly speculative but offer potential insights into the quantum nature of spacetime. The black hole information paradox highlights deep conflicts between quantum mechanics and general relativity that become apparent when considering the fate of information that falls into black holes. If black holes evaporate completely through Hawking radiation, quantum mechanics demands that information be preserved, but general relativity suggests that nothing can escape from inside an event horizon. Recent theoretical developments propose that information might be encoded in subtle correlations between outgoing radiation particles. Wormhole physics explores hypothetical tunnels through spacetime that could connect distant regions of the universe or even separate universes. While traversable wormholes would require exotic matter with negative energy density to remain stable, they represent exact solutions to Einstein's field equations and illustrate the remarkable flexibility of spacetime geometry. Even if such structures don't exist naturally, studying them deepens our understanding of causality and spacetime topology. The firewall paradox in black hole physics asks whether infalling observers would experience a violent firewall of high-energy radiation at the event horizon or pass through smoothly as general relativity predicts. This puzzle arises from attempts to reconcile black hole thermodynamics with quantum mechanical requirements for information preservation. Different proposed solutions have radically different implications for the nature of spacetime and the relationship between geometry and quantum information. ADS/CFT correspondence represents a concrete realization of holographic duality, showing how a theory of quantum gravity in a curved spacetime can be exactly equivalent to a quantum field theory living on the boundary of that space. This duality has provided unprecedented insights into both quantum gravity and strongly coupled field theories, suggesting deep connections between geometry and information that may be fundamental to physics. Quantum error correction codes reveal how information can be protected against decoherence and noise through redundant encoding across multiple physical systems. Recent discoveries suggest that spacetime itself might employ similar error correction mechanisms to maintain the coherence of quantum information, with implications for understanding how classical geometry emerges from quantum foundations. These connections between information theory and gravity represent some of the most exciting developments in theoretical physics. Consciousness and cosmology intersect in subtle ways that challenge our understanding of observation, measurement, and the role of awareness in physical processes. The fine-tuning of cosmological parameters for the existence of complexity and consciousness raises questions about selection effects and the anthropic principle. While consciousness doesn't appear to play a fundamental role in cosmic evolution, its emergence from cosmic processes represents one of the universe's most remarkable achievements. As these cosmic perspectives settle gently into your awareness, they create a profound sense of connection to processes far grander than individual experience, yet intimately related to every moment of consciousness. The universe's patient creativity across billions of years provides the ultimate context for understanding our temporary participation in cosmic evolution. Sleep becomes a form of synchronization with these deep rhythms, allowing consciousness to rest within the same fundamental patterns that organize matter and energy throughout space and time. The mathematical elegance underlying cosmic processes suggests that the universe operates according to principles of extraordinary beauty and coherence, from quantum field equations to the geometric relationships that govern space-time curvature. This mathematical harmony creates a sense of cosmic order that transcends human understanding, while remaining accessible to consciousness through the same neural processes that emerge from billions of years of cosmic evolution. Tonight, as you drift into peaceful rest, remember that your awareness represents the universe becoming conscious of itself through temporary arrangements of matter and energy that trace their origins to the cosmic dawn. In sleep, these ancient elements continue their patient work of maintaining the biological complexity that makes consciousness possible, participating in the same fundamental creativity that brings forth stars, galaxies, and the endless emergence of novelty throughout cosmic time. Rest peacefully in the knowledge that you are intimately connected to cosmic processes that operate with such elegant precision. They create stable conditions for complexity, consciousness, and the ongoing exploration of possibilities that may have no limit. The darkness of sleep mirrors the cosmic darkness that provides the backdrop for all illumination, while dreams might echo the universe's own creative processes of generating new patterns from the infinite potential that underlies all existence. And so our gentle journey through the cosmos draws to a quiet close. We've drifted together through discoveries that reveal space not as the cold, empty void we often imagine, but as a realm of profound interconnectedness and mathematical harmony. From the patient rhythms of planetary formation to the whispered messages carried by gravitational waves, each revelation has reminded us that we participate in processes far grander than our daily concerns, yet intimately connected to every breath we take. The universe continues its ancient dance while you rest, expanding with such elegant precision that distant galaxies follow predictable paths across billions of years. Quantum fields fluctuate gently throughout space, maintaining the stability that makes existence possible. Stars are born in stellar nurseries with the same patient creativity that has operated since the cosmic dawn, while consciousness itself represents the remarkable achievement of matter organized into awareness. As you settle into sleep tonight, carry with you the knowledge that you are made of elements forged in the hearts of ancient stars, temporarily arranged into the extraordinary complexity that allows you to contemplate your cosmic origins. The same physical laws that govern the expansion of space also organize the neural networks in your brain as it processes the day's experiences and prepares for tomorrow's possibilities. If you've enjoyed this peaceful exploration of our cosmic neighborhood and would like to join us for more nighttime journeys among the stars, feel free to like and subscribe. Share your thoughts about which space discoveries brought you the most tranquility in the comments below. Until our next voyage together, rest well in the gentle embrace of cosmic time, knowing that you are forever connected to the infinite creativity that brings forth galaxies, consciousness, and endless wonder. Sweet dreams, and may you drift peacefully through your own inner cosmos.